So, we have seen the classical theory for metal to explain different properties, and we have seen this. It is successful partially, but it has also remarkable failure. So, as I mentioned that we need to treat this metal using the quantum theory. Okay. Quantum theory for metal. So, basically this free electron gas it is true, it is there in metal, these free electrons are there. So, it may not be completely free, it may have potential, but weak potential. So, but main thing is that this free electron gas, it is there in metal. We can treat the metal as a source of free electron gas. Now, the failure of this classical theory is basically here these electrons, it is considered like a gas atom in gas form. So, atoms was neutral, whereas the electron have charge. So, that is the big difference, and for free electron gas, it is classical, because in this case the Maxwell-Boltzmann statistics was used, right. So, this basically classical statistics. Here in this case, there is a distribution of particle of electrons, energy distribution or velocity distribution. So, whatever the distribution, say energy distribution, so that distribution is basically following the Maxwell-Boltzmann statistics. It was taken that distribution. So, in this case it may have this electron gas will have all sorts of energy. It can take, so it will be distributed among the continuous energy, and statistics will tell this what is the how many particles are there with a particular energy, or in a particular energy range E to E plus d E. So, how many particles are there. So, that depends on temperature, but at 0 temperature, if you consider 0 temperature, then this all electrons will try to go to the lowest energy level, to minimize the energy of the system. So, thus this classical statistics allow this all electrons to go to a lowest energy. Okay. So, that was the problem, because it is not allowed for electron. Electron is Pauli exclusion principle. Pauli exclusion principle will not allow all electron to go to a one energy level, right, to have the one energy. So, this this Pauli exclusion principle is very important, and you have seen this in case when I taught you about the atom. So, these electrons are distributed among the orbits or orbitals. It strictly follows the Pauli exclusion principle. So, this free electron gas, there these electrons are treated just like gas particle, and it can have the all electrons can be put in a energy level, or as many as electron one can put in energy level. So, that is not allowed, because it is not gas particle, it is electron. So, it will not follow the Maxwell-Boltzmann distribution statistics. So, mainly that was the problem with this model. So, it is a Fermi Dirac statistics is the right choice for this electron gas. So, that was the main difference between the classical theory and the quantum theory for free electron of metals. Okay. So, but quantum approach, so quantum mechanics or wave mechanics, quantum mechanics or wave mechanics so it has own language. It is quite different from the classical mechanics. Okay. So, hopefully you started to be familiar with this quantum mechanics, but I will try to use quantum mechanics from the basic. So, let us just tell me few words about the quantum mechanics or wave mechanics. So, quantum mechanics or wave mechanics, you see this and classical mechanics, main difference is that this classical mechanics is basically one can take continuous energy is continuous, any energy particle can take, any velocity particle can take, etc. Okay. So, continuum. Continuous, and quantum mechanics is basically discrete. basically this. So, you have seen from both theory that electron or orbits cannot take any energy, it can take only particular specific energy. Okay. And so, that is the main one difference. And another, in case of quantum mechanics, so momentum and position of particle we cannot determine simultaneously. So, if you determine one precisely, so uncertainty will come to the another one. Okay. So, but in classical mechanics it is, so one can determine position as well as momentum accurately simultaneously. So, these are the things are there, right, and this quantum mechanics is basically it's deal with probability and that one has to find the probability of staying a particle at this position, or to have the momentum some value. Okay. So, that is the probability. It is not always, it is not only that value, it will have this only that value, that is accurate value. Okay. But we can only find the probability. Okay. Under this situation, this particle can have position in this place, or it can have the momentum of this value or energy of this value, etc., etc. So, it is a probability. So, it is not one has to find out the probability. Okay. So, now for free electron gas, in our topics free electron gas, for free electron gas, so how to apply quantum mechanics, so that we have to see. So, this is as I told, this quantum mechanics or wave mechanics, we tell wave mechanics. Okay. So, wave mechanics, and so this, so light is a wave. Light is a wave, or X-ray is a wave, right, light or X-ray. So, in general electromagnetic wave, electromagnetic radiation, so it is known as a waveform, wave. Okay. And it is expressed in terms of wavelength. Wave means it has wavelength, right. And particle, either on electron or on gas molecule. So, these are basically we consider them as a particle. Okay. They are particle. Electron is a particle, neutron is a particle, proton is a particle, atom is a particle, right. Neutron is a, so it can be electron, it can be neutron, it can be proton. So, it is a particle. So, particle means it will have mass, right, it will have mass, it will have momentum, it will have momentum p, momentum, that is basically mv, right. So, its particle, when we tell particle, so particle have mass. When we tell wave, we tell wave don't have mass, but it has wavelength, right. So first time it was that Planck mentioned about the quantization in terms of some, so this some Planck constant h. So energy of that quanta, okay, this h nu. So this is the energy. So that electron have, so this light or X-ray, it is wave, its if it is frequency is nu, then or wavelength is lambda, then light velocity c, so c by lambda, so that the frequency nu. So h c by lambda, that will be the energy of what? Energy of what? So energy of photon. So light, it is well known as a wave, it has wavelength, but this light also it can be treated as a this whole light, whole wave, okay, it can be treated as the propagation of the quanta. So that is called photon. So it is the propagation of the photon. So it is a discrete nature of this wave, okay. So that's basically called the photon. So it's just like as if it is giving flavor of the, particle. So this wave or light X-ray, it can have particle nature. If you consider it, then only you can write that energy of this, not wave, energy of that then photon. So part of the wave. So it's as if it's quantized, make a quanta, many quantum size of the portion, and that we tell this photon, and this photon, each photon will have energy E equal to h nu or h c lambda, right. And that, and from Einstein's mass energy relation, so E equal to m c square, okay. If any particle is moving with velocity, with light velocity, with velocity c, so its energy will be m c square, okay. So from here if you can see that I can write this equal to h c by lambda, and this is giving m c. So from here I can write this m c equal to h by lambda. So m c mass into velocity, this is momentum, right. So I can write this p equal to h by lambda, right. So this with light, one can see that one can get the momentum of that light, that is p. So as if this wave also has mass, okay, that feelings, it is giving that feelings. Waves also have mass, okay. So its mass have only this for particle, right. When we consider particle, so it is, we accept that it has mass. When in case of wave, we accept that it has wavelength, but in case of wave, it will have the momentum, it will have the mass. So, that is not in general, it is not accepted, but it is the case from here. So, these two, both these two are well, this one and this one. So, I can write E equal to h nu, and then this. So, these are these are the these two relations are very famous, and if we just go ahead with these two energy for wave electromagnetic radiation, say for light. So, we reach here. So, as I told, momentum is basically it's the parameter for particle, and wavelength is a parameter for wave. But in case of wave light, here we are saying they have relation P equal to h by lambda. Okay, as if from here we can tell that wave has dual nature. It has wave nature as well as it has particle nature. Okay. So, duality, dual nature of wave. Right. So, now de Broglie it extend this he extended this concept for matter. De Broglie extended this concept for matter. Okay. So, he mentioned that matter material or particle may have also the wave nature. So, that is called generally matter wave or particle behave also like a wave. It has particle nature, also it has wave nature. Okay. So, just extending this concept for particle, de Broglie mention this about the matter wave, and it will follow this relation. If matter have the momentum p, then wave associated with this matter will be this wavelength will be lambda, and they will be related like this. Okay. So, that is why this lambda is called the de Broglie wavelength. Lambda is called the de Broglie wavelength of matter. So, now this free electron gas, electron is particle. Okay. Now, electron is particle. So, now electron can be treated as a free electron, it can be treated as a wave also, right. So, it will have the wavelength lambda equal to h by p. Okay. So, that means for this free electron gas we can use wave mechanics, or that is quantum mechanics. Okay. As I mentioned, this quantum mechanics is called also wave mechanics. So, it is wave mechanics. So, either it is quanta or it is wave. Okay. So, quanta means quantum. So, quanta from quanta means this it is particle quantized quanta, discreteness. Okay. It is not continuous. So, thus here I just try to justify that free electron gas, it can be treated as a wave. Okay. So, wave mechanics, that is quantum mechanics, can be used for this free electron gas. So, now free electron, it is in a inside metal, and I mentioned earlier that electrons are completely free inside the metal, and we can take the potential energy of electron is 0 inside the metal. Okay. So, just consider as if this inside metal electrons are there. Okay. So, inside this potential is 0. So, if I consider that if it is in a box, it will be 3-dimensional box, right. But for simplicity, we can consider the just 1 dimension, and then we can extend for 3 dimension. So, 1-dimensional box. Okay. So, here if I put the coordinate here x equal to 0 and here x equal to L, this is the dimension of the box in one side. So, 1-dimensional case if I consider, so electrons are there. So, this potential energy, it is 0 when x is less than L and greater than 0. Okay. And potential energy is very high. So, for convenience we generally take infinity when it is just outside of this box, or it is just on the surface of the box. Okay. So, x, this when x is greater than equal to L or less than equal to 0. Okay. So, this we have. So, when we consider, because we mentioned that because electrons are in metal, and that electrons even at room temperature they do not come out from the metal. Okay. And simultaneously we are seeing that electrons are free inside the metal. So, that means its potential is very small or 0. Okay. But it cannot come out, that means that on the surface it will have the high potential. So, it will act as a potential barrier. So, this is the realistic situation for electron gas, for electrons in metal. Okay. Now, that we are just considering that now electron is in a box, 1-dimensional box, its length is L. Okay. And this outside it. So, this edge is a, okay, here this potential is very high, is infinity. Outside here also potential is very high, infinity, whereas inside within this length potential is V equal to 0, okay, in this range. So, thus that we have taken a here, you can take this as a just analogy. Okay. Whatever we have real system. So, compared to in comparison to that we have taken for calculation, for the purpose of calculation we have taken this box model, okay, and initially we have taken 1 dimension and we can extend this for 3 dimension. Okay. And now we have to use this Schrodinger equation. So, wave mechanics, quantum mechanics, so it is based on the Schrodinger equation. This is a Schrodinger equation, right. What is that Schrodinger equation? That is minus h cross square by 2m d2 psi say n by dx square, right, plus potential energy equal to total energy, right, equal to total energy. Okay. This is this total energy, this for nth, this n we have. So, I will tell you. So, for nth state, energy of nth state. So, here we have considered the potential energy 0 inside the box. So, we are treating the system inside the box. So, then your equation become d2 psi n by dx square equal to so minus is there, I can take 2 m e divided by h cross square okay. So, here also because psi is there. So, here whatever V x I wrote. So, here also we have to put psi. Okay. So, this part 0. So, this I can write in psi n equal to 0, right. So, this the I have written Schrodinger equation in general, then I have to adopt that equation for my system, and this is the equation. Okay. So, if I take this as a one parameter 2m n by h cross square equal to some k square. What is k square? That we will see. So, I can write then this is a k square psi n, right. Now, this you see this I do not know, you must be familiar with the spring mass system when it is oscillating. So, if you set equations, it comes like this, right, and its solution is general solution. One can write psi n equal to a x sin k x plus b cos k x, right. So, this is the general solution for this Schrodinger, for this equation. So, this basically now it is the solution for our system. Now, for in quantum mechanics everything this psi n is a wave function which contain all information about that system, right. So, now one has to extract all information from this wave function, and wave function we have to adapt with our system, putting the all conditions, right. So, what are the conditions here? That we have to see here. This particle cannot go outside, electron cannot go outside. So, now we will not talk about the electron. In quantum mechanics it is not electron, it is a wave function. Okay. So, we are telling wave function means it is whatever it is, it contains all the information about this system. So, instead of telling electron, we will tell the wave function of this system free electron gas. Okay. Now, so electron cannot go out means here we will tell psi cannot go out, psi cannot go out. So, always it will end here, start here and then see any it's basically wave. So, it can be like this wave, this function wave function psi n, it can vary like this, it can vary like this, it can vary like this, right. So, here we have to put the condition because we have to be realistic, right. So, psi n will be 0 at x equal to 0 and at x equal to L. So, this is the condition, boundary condition. So, this is the general solution. Now, we have to apply this boundary condition and find out, we have to make more particular for our system. So, I will stop here, we will continue in next class. Thank you.